Good morning. So, welcome back to class. We'll finish up our discussion of gravity today, or the chapter on gravity today. Go through a few example problems and hopefully kind of give you all tools that you would need to answer any of the remaining questions in the homework. Kind of a smaller crew. I'm gonna wait a second here and see where everybody is. But does anybody have any questions or thoughts, concerns before we kind of get started? Let's see. I didn't need to do chapter 2 and 3 corrections, but I lost 50%? Huh. It's probably just a glitch with the grade book. Yeah, let me know if you notice. Somebody else had pointed out to me there were some glitches between the homework system gradebook and the Blackboard gradebook. Those systems don't work super well together. So point that stuff out to me and I'll get it straightened out. Um, yeah, you're under no obligation to do the corrections. That's totally an optional thing. If you do the corrections, you get the average. Is the way that it's supposed to calculate that. Um, I'll make a note of that right now here. Yeah, we're not going to let anything like that negatively, impact your grade. It's got to be, it's some sort of an error. We'll get it straightened out. So yeah, thanks for bringing that to my attention. Um, let's see, any other questions or anything? Okay, well, we have kind of a few different topics to talk about today, so we'll go ahead um, and get started. If you have questions, additional like logistical questions, what's the Earth's mass? I think it's 5.98 times 10 to the 24 kgs, if I recall. But that's the kind of number you can get, you can look it up and write it on a post-it or something. Ah, for the homework. Yeah, I mean, you can Google what the Earth's mass is. My opinion on things like knowing constants is that, yeah, I mean, you don't want to have to memorize a whole bunch of different numbers. That to me seems like the kind of stuff that you want to be able to look up. So if I was to give you a problem, say, if we were in class, say, right, you would always have that provided as part of your problem. I wouldn't expect you to memorize something like that. Let's see. And since you're doing stuff on the computer, you can always look it up. What I don't want you to do is look up like, hey, how do I solve this problem? Because then I think you're kind of shortchanging yourself. Because what we really want to do is build up our problem-solving skills, and that can't be replaced by Google. You know what I mean? So let's see. I like the Blackboard problem. Yeah, we'll see. I'm gonna look at those and see how. My hope is that then I can give you some better feedback because one of the flaws with the doing stuff online is that it's all or none, right? You don't know. It doesn't give you any feedback. So we have that in the mix and we'll see. Hopefully that helps. Okay, so let me switch back to our whiteboard. So we're talking a little more on gravity today. Um, one topic that we didn't get to last time, it's a real quick topic, but it's kind of neat in that it connects with some stuff that we've done before. And there's a homework problem that is directly about this issue, and that is these problems that ask you something like, you're in an elevator, you're standing on a scale. What does the scale read in various circumstances? So we're going to work through an example of that. Um, And this connects with gravity because it's related to weightlessness. So this is in section 6.4, if I recall, and it's relevant to this idea of something being weightless or weightlessness. Okay, so let me kind of give you a cartoon of what we're thinking about here. So the first, we'll consider some different combinations, some different scenarios. The first that I want you to think about is basically if you're stationary and you're standing on a scale. So I'll draw that as a box and like imagine there's like a spring or something in it. There's going to be, your weight that's pointing down on the scale. And then the scale is going to push back. And we've been accustomed to calling this the normal force, but I'm going to call it Fs for force scale. And I'm calling it that just to explicitly make the connection that the scale is going to read the force that it's going to push back on you with. Okay? And we'll have some coordinate system. This is a one-dimensional situation in the y direction that we're considering. And so, when we go and consider sum the forces in y, what are we going to have? Well, we'll have the force that the scale on the scale, not on the scale, the force that the scale reads. And this is what we think of as when you step on the scale, your weight is what the scale is telling you, right? So that's positive. The force of gravity, mg, is negative. It's pointing down. And that is going to equal the mass times the acceleration in the y direction. But in this situation, if we're stationary or, constant v, there's no acceleration, so this would be 0. And so when we go and look at this, the scale is just going to read mg. And this is, this is our what we think of when we think of weight. So this, I'll just call this like, the regular weight. This is what we, regularly think of. Okay. Now, where we can add to this picture is suppose, now it's kind of silly to imagine, but it's, you can do this thought experiment. Suppose now that your scale, like a spring or something, is in an elevator. And let's imagine that that elevator is accelerating upwards. And the magnitude of that acceleration is going to be 1/2 of little g. Now, in this situation, what are the forces? Well, you still have mg, the force of gravity pointing down. The scale is still going to be pushing up with some force. And then those are the forces that are present. When we go to sum the forces, though, we have the force on the scales pushing up, force of gravity pushing down. In this situation, though, this acceleration is not going to be 0. The acceleration will be 1/2 g. So in this case, if I solve for what the scale reads, you'd have mass times 1/2 g plus mg. So, and it's 1/2 is positive because it's pointing up. The g is just telling us the size, the magnitude of that. So, in other words, this is 3/2 mg. So it's, 3/2 of our weight, what we normally think of. And another way that this is often depicted is that this would be, like 1.5 or 3/2 G's. But yeah, let's call it 1.5 G's, right? i.e., it's larger than just the acceleration due to gravity. And you can probably, you may have some intuition about this if you're in a situation where, like in a car or something, and you really mash on the accelerator, you may feel pushed back in your seat a little bit. You're adding to that. So in an elevator, you can feel that sometimes, but it's kind of difficult unless because elevators are designed to not have large accelerations. Let's see. Yeah, this is just an example. So this is just for sake of example. Suppose that the acceleration is 1/2 g. Okay. So, and then you can imagine where this is going. We can look at also the other scenario, which is, let's say you're in the elevator, and now instead of it accelerating up, let's have it accelerate down, but with the same magnitude. Okay. And the picture does not change. Forces are still present. Weight, the force present on you from the scale. We go to sum the forces in y, scale, minus the weight. But now, instead of that acceleration 1/2 g being positive, it's going to be negative because it's pointed down. And when we solve for what's on the scale, notice we'll have negative 1/2 mg plus mg. In other words, this will be 1/2 mg. I.e., the scale is going to read 1/2 your regular weight. Or you can think of that as you're pulling, you only have half of a g. And then, of course, the real extreme example of this, and where this connects to what we're talking about in this chapter, would be not extreme, but just kind of the limiting case would be, suppose that you're accelerating down at g, i.e., in free fall. The elevator cable has snapped or something, and the elevator's falling. Same cartoon, you're standing on a scale in there. Your weight or your force of gravity is pulling down on you. The scale is pushing up. We go to sum the forces in the y direction. Force on the scale minus the force of gravity is going to equal m times minus g. The acceleration, the same size as gravity and pointing down. Now in that situation, when we go to solve for the force on the scale, you're going to have negative mg plus mg. It's going to equal 0. So in other words, in this situation, you're in free fall. You're 0 times your regular weight. You're weightless. Okay? Except I spelled weightless wrong. And something that's kind of cool about this, if we were on campus, is if we were on campus, we would look at this with Firefox, because what you can do is you can ride an elevator and watch the accelerometer in an elevator, and you can observe these modifications to g as you accelerate up or down. So you can look at this experimentally with Firefox, and you can do a mini experiment at home. So what you do is just take your phone and drop it onto something soft while you look at the acceleration. Look at the accelerometer with gravity tool option in there. So when you watch that, by default, it's going to give you a plot of the acceleration that it sees with time. And normally, it's going to kick around about 9.8 because it's detecting gravity. So there's a little mass that's in there. It sees how the mass is pulled down by gravity, and you will see 9.8 on your phone. Now, when you drop it, though, what you'll see happen is it'll be reading 9.8, and then it should go basically to 0, and then it will hit, and you'll see like a bunch of noise, and then it'll go back up to 9.8. There's a big acceleration when it hits, and it'll look weird, but while it's falling, it can't detect it. So it's kind of a cool tiny experiment that you can do with your phone to test this idea of weightlessness. So basically, it will appear weightless while falling. And like I said, if we were on campus, we could play around with like the elevators, like in the new building. Some students did that last quarter, and they found that it worked pretty well to read they could see modifications in G by riding the elevator as it accelerated. So, anywho, there's a question in the homework that this is directly relevant to. So hopefully this kind of clarifies a little bit the what they mean by these problems where you're in an elevator and you're standing on a scale, etc. So, y'all have any questions about this situation? Please extend this concept to applications in civil engineering. I dropped my phone on a pillow and it broke. So with regards to civil engineering, are you yanking my chain? Is this not a? It's tough to. I'm not sure. I'm not sure. Things don't drop things that aren't meant to be dropped, I guess. Anthony, did you actually do the? Did you try it? Were you able to see gravity go to 0, or are you? So yeah, no, serious. Look at it on Firefox with this accelerometer with gravity option. Here, I'll draw a red little box around this. It's kind of cool. Yeah, so cool. Yeah, the gravity will go to 0. So it's a statement of the fact that your phone, it can't tell when it's falling. It's weird because it's accelerating, right? It's not like gravity is not there, but it needs to be measured relative to something. So when it's sitting on the table, you can detect that relative to the table. It's like you're measuring, it's like you have a scale. But once it drops, there's no longer anything to detect against, and so you can't detect it anymore. So it's directly analogous to the situation, these scale problems. Familiarizing yourself with the accelerometers in the phone is kind of a fun exercise, and we may use that for a future lab exercise if I can come up with a good way to do it at home. So okay, tell you what, we can come back to this. I do definitely want to encourage these kinds of things where you can play around with something on your own. But I want to spend some time talking about how to solve some problems, and that'll be useful for everybody as we in the homework and everything. So let's change gears and talk again about orbits. Actually, so back to orbit problems. This will be pretty relevant to the homework. It does go to 0. Cool, cool, cool. Yeah, so other folks, try that out when you get a second. It's pretty neat. So let me pitch to you a couple example problems. So this is kind of a conceptual problem, but I like it in that it gives us an excuse to re-emphasize the role that gravity is playing in these situations. And we also talked about geosynchronous orbit yesterday, so you kind of have in your mind what that's about. Recall, so the question is, why is it not possible to launch a satellite into geosynchronous orbit above the North Pole? So remember, geosynchronous orbit was you have a satellite that's basically it's watching a location on the equator. So as the Earth spins, the satellite is orbiting, and we figured out, for what radius you have to be at in order for that to make one orbit in one day. And the question is, well, why can't you do this above the North Pole? So in that situation, the cartoon of what that would look like would be, why can't you orbit around, have your satellite appear so you can watch a location that would be on the North Pole-ish? And what do you guys think? Why would this not work? What do you guys think? Why wouldn't this work? Yes, exactly. So the issue is um, and why I bring this up is it gives us a chance to recognize. So in this orbit, velocity would be like this. It would be perpendicular to r. The force of gravity is going to point towards the center of the Earth. So the force of gravity would be pointed like this. However, when you're in a circle, that centripetal acceleration points towards the center of the circle. So in this case, for an orbit like that, for something like that, it wouldn't be pointed in the same direction as gravity, so this would not work. Yeah, you could imagine some sort of exotic situation where the sum of the forces gave you that, and there are actually so the short story here would be that FG would not be able to provide AR because it's not pointed in the same direction. But yeah, to Ethan's comment, you'd need a constant force going opposite. So there are actually like exotic orbits. There's something called a Lagrange point where you can imagine there's a question I think in the homework that asks you to find where between the Earth and the Moon would the force of gravity, would the gravitational acceleration be the same? You can actually orbit like around those points, which is pretty wild. But that's kind of an out there topic. This is something called a Lagrange point. Um, but for this, yeah, in terms of geosynchronous orbits, you can't have them above the North Pole. You can only have this uh, about the equator. Okay. So I think that that's kind of a cool conceptual thing to think about because it just reaffirms to us that AR and FG have to be pointed in the same direction. Okay. So let me show you another more of a calculation problem. Wait. So here's one. Everybody's heard of Hubble. So the Hubble Space Telescope circles the Earth at an altitude of about 338 miles. Find the velocity and how long does it take to circle the Earth. So this how long would be what is the period. Let's see. Yeah. No, that's a cool point. So there's this sort of the telescope that's going to take over for the Hubble. This James Webb telescope that's in development is going to actually orbit around one of those Lagrange points. That's a really cool thing to look at. If you're intrigued about kind of what's going to be the next generation of space astronomy, oh man, that telescope is wild. The mirrors on that telescope are enormous. It's gonna be quite a feat. Yeah, so let me Google this if you get the chance. Thanks for bringing that up. That's a cool point of reference. For kind of a connection to something like this. To the problem at hand, so this is a little bit different than before. Before we looked at solving for the radius that we needed for the geosynchronous orbit for a particular orbit. And oh yeah, you can look up visualizations and stuff. Yeah, well maybe I'll look into that. I can post some stuff. So Kyle, you can find if you find something that's cool, post it on the like links channel. So and that way other people could see, if you find, and that goes for anybody, if you find some cool link that connects to some stuff that we've talked about, post it in there. It's so nice to think about situations that are not just right out of the book, right? Kind of broaden our horizons a little bit. So that'd be great if you would do that. Kind of bracket that for the moment. So this problem, we're talking about, we have the Hubble Space Telescope. We've been talking about how it's often easier to break this up into so this would be the radius of the Hubble's orbit, and we often can break this into the radius of the Earth plus the height above the Earth. Okay. And so for this question, how do we get started with this? Well, just like we've been doing. I think it's easiest to approach these going back to basics. If we look at the sum of the forces in the radial direction, we're going to have, whoa, GMM over R squared is going to equal M V squared over R. In this case, we're looking for velocity. Again, a bunch of this stuff is going to cancel. So we have an expression GM over R gives us the velocity squared. So if we want to know what the velocity is, of course, we would take a square root of this. And we can put in our numbers. So recall G was 6.67 times 10 to the minus 11. The mass of the Earth, 5.98 times 10 to the 24. Divide by the radius. So the radius, again, that'll be the radius of the Earth plus this altitude. So the radius of the Earth was 6.38 times 10 to the 6 meters. And the altitude, so we have to be careful. This altitude is in miles. So let's convert this by multiplying by how many meters are in some number of miles. So the one that I remember is that this 5,000 meters in 3.1 miles. So that'll keep the stuff that's in the denominator is both in meters. We wouldn't want to have, mismatched units in there. And then we take a square root of the whole situation. And this would give us, we would find that this is 7.6 times 10 to the 3 meters per second, i.e. 7.6 kilometers per second. So this gets at the fact that, we're in space. Your velocity can be really large because there's no air resistance, there's no friction. And really that's what's required to orbit. But it's numbers that are a little bit outside of our intuition because they're so big. Okay. And then, the second part, so that's basically part A. The second part of this question was, how long does it take to circle the Earth? And we usually use the letter T, capital T, to denote that. Let's see, is the 6.38 the Earth radius? Yeah, 6.38 times 10 to the 6 is the radius of the Earth. So these, like I mentioned before, these numbers, you can look these up and just keep them on a Post-it. I think you'll find in the homework and stuff which number, some like the mass of the Earth is commonly used. I think there's a chart in your book as well. And of course G. You see what I'm saying? Like you can find this stuff. This is what's good. Google is good for looking up facts like that. So in terms of this, how long does it take to orbit? I think what you can think of in that situation is if you think of a top view, for one time around, the period of one orbit will equal how far that is, so the circumference, 2 pi r, divided by the velocity, the speed really, and we just found that. If it's helpful, you can also if it's helpful to keep these straight, you can think of the velocity as the velocity is the distance over the time. So you know that distance is 2 pi the radius, the time is the period. So this is another way to derive that relationship. In any case, when you put in our numbers, so r would be what we have up here. Our velocity is this number that we just found. You get a number in seconds. So this is, meters divided by meters per second. So that'll give you something in seconds. And it's a pretty big number. 5.7 times 10 to the 3 seconds. It's kind of hard to visualize that. So putting this, dividing by 60, give it to you in minutes. This is 95.6 minutes, which is maybe a little more digestible number. So that's telling you that this thing goes around the Earth every 95.6 minutes, which is pretty wild, and it speaks to the fact that it's going so fast. If you were to imagine flying around the world or whatever, that would take, hours and hours. It would take a day or more. So why I showed you this question is just that this is another example of the types of things that you can solve. There's stuff in your homework that's like this. Find velocities, find periods for orbits. Cool. Questions? Are these concepts used exclusively in space-related problems? I don't know. It's the only application that comes off the top of my head. There are some connections. We'll talk to about this. Well, one connection actually I'll mention. So how about as an aside, there's one homework problem that's about this. It's a connection to basically PH 2011, and that is there's a question in the homework that asks you about a gravitational field, which is kind of a weird idea. But what it is we're talking about these non-contact forces, right? So you can think about, you can put in a radius and solve for how things are going to behave for a given radius and velocity, etc. And we did that, pretty explicitly in lab. Another way to think about this is to visualize what the acceleration due to gravity would look like everywhere. So a gravitational field is basically, and this is in section 6.6. So gravitational field is the force of gravity divided by, or the force of gravity per unit mass. So a force over a mass would give you an acceleration. And you can think of this as an acceleration in everywhere in space. So this idea we introduce it with regards to gravity, but this is, you'll use it a lot more with electrostatics. When you're talking about electric charges, and that comes next quarter. So that's part of why we're talking about some of these more abstract vector concepts, because they will appear again in the next quarter. It's not exactly like orbits and stuff, but it is the same math because it's this inverse square behavior. Okay, so let me show you another problem that's kind of in the vein of how you can solve for different quantities. Um, and that is this one. Ah. So far we've solved for for r, we solved for the period, we solved for velocity. Let's look at mass. And that's what we're going to do with this question. So, let's see. So this is kind of a cool question. If we were in class, what I would have us do would be to do this for these different data sets and compare. But what we have here is a table that lists some of the moons of Jupiter. So if we want to visualize this, we have, Jupiter, and these moons have different size orbits. So different radii. There's Io and Europa and Ganymede and Callisto. And we're given, the masses of each of those and the period t, and as well as the radius for each orbit. Now, what we're after here, so let me read you the question, sorry. It says table 6.3 gives the mean distance, period, and mass for the 4 largest moons of Jupiter. Determine the mass of Jupiter using the data for Io, and then determine the mass of Jupiter using data for each of the other 3 moons. So if we were in class, we would, we could break this up and have everybody try a different moon. But let's set this up, and then we'll talk about it a little bit. So where do we start? Let's sum the forces in R. We know that that's going to equal the gravitational force. I'm going to put this in general terms and just call each one mass moon. And we know that that would be the mass of the moon times v squared over r, i.e. that's what the magnitude of the centripetal acceleration is. We could, of course, cancel out all the stuff that's common. Come on. Oops. And I should really say this is the velocity of a particular moon. So notice we could then solve this expression for, I should say we don't have the velocity per se, we have the period. So let's recall that the period is 2 pi rm over the velocity, or in other words, t. let's put that in here. So we'd have 2 pi squared, that quantity squared. And then let's, we're trying to find the mass of Jupiter, so let's solve this expression for that. So we'd have 2 pi over t quantity squared. Let's divide by a factor of g. We would multiply by this factor of r, the radius of one of the moons, and so this would be rm to the 3rd power. Now, the first part of this asks us to look at it for Io. And try and keep this all on the same page here. So we could do that. We could evaluate this. So the period for Io, we would have to put this in seconds. Times 24 times 60 times 60. This whole thing squared. We would have to then multiply by the distance. (22 times 10 to the 3rd, 26). That would be cubed. This, we'd have to put in our g. And we would find that this would be 1.9 times 10 to the 27 kilograms. So significantly larger than the Earth. Just for comparison, remember that was 5.98 times 10 to the 24th. So, it's 1,000 times larger than the Earth or something like that. Or not larger, more massive. Orders of magnitude more massive than the Earth. Now, what's less important here than being able to calculate the mass, which is useful, and I think there may be a problem that asks you to do that, if I am remembering correctly. But the thing that's really interesting is that the mass of Jupiter calculated from the parameters for Io is going to be the same as what you get if you calculate it from, Ganymede or whatever. Is going to be the same as the other moons. So, in other words, this quantity, these are equal. So, because the mass is a constant, right? So, notice a bunch of this stuff would cancel if we set these equal to each other. So just looking at, say, Io versus Ganymede. Since so much of this is in common, it's not going to depend on g. It's not going to depend on this factor of 2 pi squared. We're left with this relationship that, a more general relationship, that the radius cubed over the period squared for one moon is going to equal the radius cubed over the period squared for another moon. So this is really cool because basically, since it's we can simplify it, this relationship like this. If you know the radius and you know the period for one, and you have either the radius or the period for the other, you can get it directly from this. So notice when we did it up here, we needed G, we needed the period in seconds in order for the math to work out. But down here, if you know those quantities in another unit, you can use those other units directly. So one of the advantages of this, and this has a name, this is Kepler's third law. And one of the cool things about this is it can be, I will pitch this to you as basically it's a way, an option for solving problems. You can, it lets you make use of non-SI units. So what I mean is we can rewrite this. I can rewrite it like there's different ways, of course, but suppose I multiply by T1, the T1 piece, and I divide by the R2 piece. We can also have this expressed like this. So let's put a box around this. So notice, like, suppose you knew the radii for two orbits, and you knew the period for T2, you could get T1 just by multiplying. Now, since this is a ratio of stuff, these radii could be in whatever unit that you want, and it will cancel because it's unitless. And then this could be in years, say, but it would give you a result that's in years. Looks like a chemistry formula. Yeah, so this is, yeah, I'm pitching it to you as an optional tool for solving problems. You don't have to use this, but it can help, it can simplify some things. Some problems are perhaps more easily solved using this, and it is relevant to one of the problems, at least one of the problems in the homework. So which problem was it? See, problem 6.44. You can use Kepler's law, third law, to help with this. So the natural question I think that arises when is this only true for bodies orbiting the same mass? Yeah. So this would be for, like, think of this as like moons around a planet, planets around a sun, etc. They have to be orbiting the same mass. So I think the natural question I'm throwing at you, or that may be in your mind right now, is, so this is Kepler's third law. Well, what are his other laws? So let me show you right now that. So, and I'll show you that, and I have some slides I can show you. So, don't worry, it's not a lot of slides. It's just like, it's like 3 slides. So just so you're exposed to this idea. So there are 3 Kepler's laws. Kepler's first law is basically a statement about the geometry of orbits. So, and in words, it is the path of each planet is an ellipse with the sun at one focus. So, or you could imagine the path of each moon is an ellipse with the planet at one focus or something like that. So you may have observed this experimentally in lab, where playing with orbits, you could see that for some situations, like if you tweak the velocity, you could make the orbit very elliptical. So in practice, at least analytically, it's difficult to work with those elliptical orbits. So you're not expected to do anything with that in the homework, for example. But I think it's good for you to know that that's the case and for you to have seen that in the lab. So orbits are not circles in general, they're ellipses. We usually just talk about circular orbits because it's easier to compute them. But you can imagine you can do more sophisticated things like specify how eccentric, how elliptical the orbit is. There's a parameter called the eccentricity that lets you do that. But for our purposes, it's mainly just orbits are actually ellipses. They're not circles, which is interesting. Kepler's second law, so in words, each planet moves so that an imaginary line drawn from the sun to the planet sweeps out equal areas in equal periods of time. So this is difficult to see without a visualization. So this animation shows you this. Now, there is a lot going on in this animation, but let me try and explain. So notice there's some different vectors. The green vector is the velocity. So notice as you go closer to the focus, the green arrow gets longer. That's a statement that the satellite is accelerating. It's speeding up, and so it's going faster when it's closer. Okay? The other arrows, so the purple arrow that's in the same direction as the green one, or that's pointing along the same line, that's the acceleration. So as it speeds up, see how that one appears and then it goes away when it slows down once it passes the closest approach? So that's the acceleration. Think of it as the speed in the orbit. Now, the purple arrow that's perpendicular, that's AR. That's the centripetal acceleration that we've been working with. Notice that one, when you get close, it gets really long. Why is that? Well, that's because the centripetal acceleration goes like v squared. So when v gets bigger, AR gets really big. And then that one that's on the diagonal, that's the total acceleration. So it's a combination of both AR and the tangential acceleration. So that's all what the vectors are doing. And then that little pi piece, that's a statement of Kepler's second law. So that's telling you that the amount of area per given time is conserved. So we could probably demonstrate that in lab with our simulation if we added some code. But the main takeaway is just that Kepler's second law. So you can see, when you're far away, the piece of the pie is skinny, but it's longer, and when you're close, it's fatter, but it's shorter, and the amount of area that sweeps out is the same. But this is, I think, a useful thing so you can see the different acceleration components, and it gets at the fact that in reality these orbits are elliptical. They're not circular. And in order for that to be the case, yeah, so the area, yep. Think of it as an elliptical pizza, sure. So the area swept out is the same. So that's Kepler's second law. It's difficult for us to make use of this mathematically because it would be kind of complicated, but it's cool, I think, to see that graphically and kind of have a picture of it in your mind. And then, of course, the last one is Kepler's third law. And, in words, the words for this one are almost more confusing than just seeing the math. but the ratio of the squares of the periods of any two planets is equal to the ratio of the cube of their semi-major axes. So when they say semi-major axes, you can think of that usually as just the radius, because usually we're talking about circular orbits. But it's the semi-major axis technically is the long axis of your ellipse. Okay, so that's a lot. That's a lot of stuff. I don't expect you to really have to calculate stuff with Kepler's laws, but I just want you to be exposed to them. And like I said, you can use it as a tool. It can really help you with some kinds of problems. And yeah, sorry, I don't want to step on your time here. So think of Kepler's laws as sort of an optional tool. And then it can help you with some kinds of problems. And you can read about this too. So this is section 6.5. Okay, so that's a lot of stuff. How are you guys doing? Do you have questions? Questions? So you should have examples of most everything that you're asked to look at in the homework as of now as well. Yeah. Yep, exactly. So as you encounter, questions working through problems and stuff, reach out to me on Teams or shoot me an email. We can set up a time and we can work through any questions that you run into. So sweet. Thanks for posting that, Kyle. Let's see. So if we brought more mass to Earth, would that change the orbit as the mass grows? Sure. Yeah, I think so. So, we could look at, let's see, what did we look at? We looked at this question about Hubble. So how does it depend on the mass? Well, it goes like the square root. So if you were to increase the mass of the Earth for a given orbital radius, the velocity would have to increase. Yeah, it would increase. I guess the short answer is the force of gravity would be larger because uh, uh, mg depends on the force of gravity, gmm over r squared. So if you increase the mass of the Earth, then the force of gravity would go up proportional to that. Other questions? Cool. Well, I want to thanks for your patience today. It's kind of a lot of ideas. I don't want to step on your time too much. I'm trying to be better about that, but it's so easy to go over. So I'm sorry about that. But reach out to me if you have other questions. For those who've we had in lab, I hope this gives you a little bit more analytical connection to the stuff that we did with numerical orbits. And for folks who we haven't had lab, we can test some of these ideas tomorrow, which is kind of cool. So with a program, we'll be using a numerical exercise to look at orbits. So thank you so much. I will see you tomorrow or see you next week. Don't forget to complete the homework assignment. Otherwise, have a nice weekend. Okay.